place of 1 over x. So in other words, if I put the 1 over c is delta v over q. So v takes the place of the F. So when I'm pushing something with a force F, the electrical equivalent is putting a voltage difference across the capacitors. Okay? And the charge that builds up on the capacitor is how much I stretch the spring. And therefore 1 over the c takes the place of the k. Okay? So mu c potential energy. Now, how about the potential energy in the inductors? Without the formal derivation, we can even come up with the equation here. What should be the potential energy of the inductor? If you go over here, it should take the place of the, let's see here, half mv squared. The inductor is the derivative, let's see here. The inductor should be, the equation is going to be half Li squared. The current, let's see here, the C is the equivalent, the X is the X is like the X is like the charge. The derivative of the X is the V. That's like the current. Oh, there's a little bit of it's not as equivalent as I thought here. There's a little bit of a difference here. The potential energy stored in the inductor is half Li squared. The L takes the place of the mass. And the I takes the place of the V. So if in the definition of M equals F over A, in the definition of M equals F over A, the M, I'm saying the L takes the place of the M. The force is replaced by the V, and the A is replaced by what? The di dt, right? No, it worked. Why did I say? For a second, I thought it didn't work. The L replaces the M, the V replaces the F, the A is the di dt, and then in the equation, half mv squared, L is replaced by the, L takes the place of M, I replaces the V, and di dt is the A. No, it worked. For a second there, I thought it wasn't working, the relationship. No, it's perfect. So the I is the first derivative of the Q, which is the V, and you have half Li squared. Perfect. So without actually doing the formal derivation of the potential energy stored in an inductor, I was able to just compare it with the kinetic energy, and it's the equivalent of kinetic energy in physics 1. So this is the kinetic, this is like the kinetic energy of a block, but it's the potential energy stored in an inductor, and then this is the potential energy stored in a capacitor. So it's really interesting to compare and see that it's analogous to physics 1. And then when you go to physics 2, you learn about Bernoulli's equation, fluid dynamics, right? The pressure in a fluid. It takes the place of the force in physics 1. Rho GH is the pressure at any point along the liquid. So this takes the potential, the place of the mgh, the potential energy, and then this is the kinetic energy of a moving fluid. So Bernoulli's equation takes the place of the work energy theorem in physics 1. So the Bernoulli's equation says that the pressure plus rho gy plus half rho v squared of any fluid is constant. So it's interesting always, as I've told you before, to take a global look at things and to see things from the bigger perspective. The next thing we